Now that we've covered probability, we're going to kind of start taking it to the next level. So today we're going to cover what we like to call compound events. So first off, let's have this discussion, and we have some Venn diagrams here to help us figure this out. When you consider all the outcomes for either of two events, you form a union. So if we go down here and we say the red dots are event A, the blue dots are event B, all of it together is considered to be the union of A or B. When you consider the outcomes and only the outcomes shared by both of them, you form what we like to call an intersection. So the union is everything. The intersection are the items that they have in common. So in a Venn diagram, it's that place in the center where the two events overlap. However, if these two events still happen, and we want to know the probability that something is occurring, but you'll notice that these don't overlap at all. I'm going to go a little bit bigger here. That these don't overlap at all. We can still find the probability that something happens, it's just they don't have an intersection. And this particular thing is important for us to point out as we find the probability of compound events. Now, the wording we use when two events don't have anything in common is disjoint. So that's just some vocab that should help get us through to explain what we're going to be finding the probability of. So, like I've said multiple times, when we look at two events, their union or intersection, we're talking about what we like to call a compound event. Now, this is different than something happening over and over again in a specific order. This is still one probability, but we're going to put multiple items together in figuring out that one probability. We're actually going to do disjoint first. So, if we have disjoint events, and we want to know the probability of A or B. To find this, you take the probability of the first event and you just add it to the probability of the second event. So kind of like we were discussing up here with our Venn diagram, I have two events, they don't overlap, so to find the probability of one or the other happening, I would just add the probability of each together. You're going to notice in this lesson, this or that you see here translates to a plus sign in between your two probabilities. Now, in this particular lesson, and I'm going to pull this up, they're going to refer to, and it was kind of hard to steer clear of it, a deck of cards. So if you've never played cards or you're not as familiar, just just Google search a standard deck of cards. If you want to place it somewhere so you have it. Here's a standard deck of 52 cards. We have 4 suits. I'll give you kind of a little background. This suit is diamonds. This one's clubs. Then we have hearts. And then we have spades. Each suit has 13 cards. The face cards are the ones that legit have faces. And when you download this, it may not be a bad idea to get one that's in color, because sometimes it'll say what's the probability of a red or a black card. So it may not be a bad idea to have it in color. So we would like to pick one card from a standard deck of cards. We want to know the probability that the card we pick is either a 10. So this is event A. Or, that's important, a face card. This is event B. And let me go ahead and color code that so that we can keep them straight. All right, so first let's find the probability of event A, which we're going to say is drawing a 10. Probability of getting a 10. So if we go over here and look at our deck of cards, the 10s are all right here. So there's 52 total cards, and 4 of them are 10s. So our probability is our favorable of drawing a 10, which is 4, out of the possible cards we could draw, which is 52. So this is the probability of drawing a 10. That's event A. Event B is a face card, which I'm just going to shorten down to FC. All right, so if we look at the face cards, they're here at the end. The reason we know these two things are disjoint is because of the fact that none of the cards that we're picking from overlap. So these 12 cards don't have anything in common with the 10s that we had earlier. So face cards, there are 12 of them out of our deck of 52. So if I draw one card out of the deck and I want to know what's the probability it's one or the other, and they're being disjoint, that means I just need to take 4 over 52 and add it to 12 over 52. Now, it may be tempting when you write these probabilities to write them in simplest form or as a percent. But what you're going to want to do is leave them in these unsimplified fractions. And once you've combined them together, because when we add fractions, we have to have common denominators. Once you've combined these into one fraction, then go ahead and simplify it. So we should get the probability is 16 over 52. Remember, you have multiple ways you could give the answer. So the simplified fraction would be 4/13. You could put it as 0.31, or you could say 31%. Now, there's a quicker way to potentially tackle this problem. Knowing they're disjoint, you could literally just initially add up. Let me go ahead and pick a different color here. You could just add up the numbers that are either 10 or a face card, and you could have gotten to 16 that way as well. So when you're working with compound events and they don't overlap, it could just be as simple as just adding up all the cards that are favorable, which in this case was 10 or face, and then just going straight to this. So there's a couple ways to get there. You'll notice your book doesn't always give you a background to what the probabilities represent. They just give you numbers. So in that case, you would want to go ahead and add it up like this. These formulas will be very helpful when your book just gives you values that represent each probability. And then it might be a little easier to actually do the story problems because you'll have a little bit of context. All right, so that's what it looks like when you tackle a compound event. So again, we're just drawing one card, but we have multiple things that are favorable. So we're adding those together in our numerator. So let's look at what happens when our events actually overlap. So you're going to notice the first part of this formula is the exact same as what we used for disjoint. However, if these overlap, we don't want to count any favorable items more than once, because then our probability won't be accurate. So what we're going to do is, if we know two things overlap, we're going to subtract out the values that are both. And this is the way that we're going to, actually I'm going to write the word and. This is the way we're going to make sure that things don't get counted twice. So this little piece here at the end, it represents the intersection of the favorables. Oopsie, ran out of room. 2 seconds. So we're going to do the exact same thing we just did, but then, knowing it's not disjoint, we're going to subtract out the overlap. If ever your intersection is 0, you can assume that they are disjoint. All right, so I'm going to copy and paste my little photo here so I can use it again. Let me go ahead and erase off the highlighting there. All right, a card is randomly selected. Again, we're just drawing one card, but we have multiple favorables we're looking for. We want to know the probability of a face card. So there's your event A. Or a spade. So there's your event B. So again, if we're to go over here and highlight the items that we have, face card, and I'm going to try and keep this in the color scheme. Face card are these 12 cards here. Spade are these 13. So again, if you wanted a shortcut, you could just add all these up and just make sure you don't count these 3 twice. However, your book, again, does not always give you context behind this. So let me show you how you can tackle this when you just have values. So the probability of a face card, which we just did above, but we can do it again here, there's 12 out of 52. The probability of a spade is 13 out of 52. And again, if you don't have these numbers memorized, how many there are, you can just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The more you play cards, the more these numbers come out to you, but some of you may not have that. So that's why the picture can help, so that you can count them out. All right, however, we know that there is overlap. So the probability of a face card and a spade is 3 out of 52. So we do have an overlap. Let me kind of shrink these in so I can put them more next to each other. So what we're going to do is we're going to add these first two together. And then we're going to subtract this one. So we should have 12 plus 13 minus 3. Again, resist the urge to simplify any of those fractions before the end because you want common denominators. And we should get that we have 22 out of 52. Oops, that's not simplest form. 22 out of 52, which simplifies eventually. I'll just go ahead and mark the answer to 11 out of 26. So if this was a multiple choice on your quiz or a test, that's what you would be searching for. If at all on a test or a quiz I ask you to do probability and it's card related, I will provide the picture for you in case you are not familiar with a deck of cards. If you ever want to pull out a deck of cards, feel free. So this is the probability of finding compound events, meaning, again, it is one event. In both of these cases, example 1 and 2, you're just drawing a single card. However, you're looking for multiple favorable outcomes. So it's not just one thing, just tens or face cards. You're saying 10 or a face card. All right, so you just add those together, but again, you're still just drawing one card. But you're increasing the likelihood that it might happen because you're increasing the number of options that are actually outcomes that are actually favorable. All right, so let's move on to this next one. It is possible that in your homework, they're going to give you parts of this formula that they'll actually give you the final answer, and you're going to have to use that final answer to actually find either the probability of event A, event B, or their overlap. So out of 200 students in a senior class, 113 students are either varsity athletes or on the honor roll. There are 74 seniors who are varsity athletes and 51 who are on honor roll. We want to know how many are on both. So this use of or and is telling you overlap versus just the sum of. So right here, they're telling us the final answer. Whoopsie. So this represents the probability of varsity or honor roll, which they gave us as 113 out of 200. So that's actually the final probability. But we're using this information to figure out the overlap. All right. So in our formula from the front page, the probability is each separate probability. So we're going to want to know the probability of varsity. And we're going to want to know the probability of honor roll. And we're going to add those things together. The number here that we're trying to find is this overlap. What we don't know is how many kids are both varsity and honor roll. So when you solve this in your homework, you can just put a variable here, question mark. I'm just going to put an X to represent that that's what we're trying to find. So if we look in our information to find these other two probabilities, there were 74 seniors that are varsity. So the probability that a senior is varsity is 74 out of 200. The probability that they're honor roll, I believe, is right here. And that was 51 out of 200. And now we want to know what is X. So if you add up 74 and 51, you should get 125. I'm going to kind of work this problem over here to the side. So I want to know what number out of 200 is going to give us the overlap. So 125 minus what will give us 113. And your answer should be that the probability of varsity and honor roll is 12 out of 200. Now again, you can give these final answers as a simplified fraction, or you can give them as a percent. This one, if you simplify it down, is 3 out of 50. So again, your book may not always give you context. So they may say, this is the probability of this or this, which is that final piece here. They'll give you individual probabilities, the probability of event A, probability of event B, and then probability of an overlap. But any one of these could be missing, and you would use the other numbers you have to solve. So even though it may seem silly to have this formula down, it's not a bad idea, because then you can just substitute what you know and solve for the part that's missing. Which leads us to this last piece. So let me shrink this down a little bit so that it doesn't take over this next part. All right, the complement. So when two things complement each other, it means they complete each other. And sometimes it's easier to actually find the complement of an event to assist you in actually finding the probability. So first off, let me just give you the notation. So when we discuss the complement, it looks like this. So the probability of A with a line over the top. To find the complement, you just take 100% or just 1, and you subtract the probability of A. One of the examples I like to give, which is probably one of the easiest to understand, is if I tell you there's a 30% chance it will rain, the complement is the percent chance it won't rain. So if there's a 30% chance it will, then we could deduce that there's a 70% chance that it would not. So those are complements of each other because they add up to the whole. Now, here's another example of when you potentially could also Google search all the possible combinations of two six-sided dice. So if you wanted to go, there's my picture that I grabbed for the deck of cards. But you could also say 2 6-sided dice. Look at your images, and you should be able to easily find. Sometimes I find it's easier to pick something like this. I'm going to copy that and bring it into the notes so we have it for purposes of figuring out what's happening. All right. So the sum is not 6, is what we're trying to find. Now, we could add up all the sums that aren't 6. However, it might be easier for us to actually determine how many add up to 6 and subtract that from 1 instead. So we could find the probability that a sum actually is 6. So it's just another way to approach it. You wouldn't have to use it. Probably one of the most important parts of this is, one, to understand what a complement means and understand the notation. Again, the book might just give you numbers. It won't actually give you context. So when you see this notation, you know it just means I need to subtract the value I have from 100 or 1, 100% or 1, and that will give me my complement. All right, so if we want to find how many of these, so we rolled 2 6-sided dice, we want to know the probability they don't get a 6. However, we think it might actually be faster just to figure out which ones are 6 and subtract that. So if we look through, 5 plus 1 is a 6. And I believe when you look at these images, they always go on a diagonal. 4 plus 2, 4 on the first die, 2 on the second, 3 and 3, 2 then 4, and 1 then 5. So if you roll 2 6-sided dice, there are 1, 2, 3, 4, 5 ways to get a sum of 6. So if it's easier to count that then instead of the other, we can just say, okay, 5 out of 36 options here. And if you put that in your calculator, you get your answer is 31 out of 36. So it's just trying to give you an option to get to your answer quicker by knowing that you have a complement. So again, if we're asked to find the probability is a sum less than or equal to 9, it might actually be easiest to just take 1 and subtract the probability that a sum is greater than 9. So that would be the complement of less than or equal to would be greater. Oopsie. So I'm going to switch colors up a little bit here. Let me switch to this. Sum greater than 9. So if you look at how this is formed, the largest values are down here. So that one's 12. These two are 11. And these 3 are 10. So if we want it to be larger than 9, there are 6 options. So if we do 1 minus 6 over 36, we should get 30 over 36, which simplifies to 5/6. The probability of getting a sum less than or equal to 9, which is actually very likely. Both of these cases, it was very likely to roll what they wanted. All right, so that's your complement. So again, it's this usage, when they don't give it context, it's this usage of this bar over the top of what you're trying to find the probability of. That's what you read as the word complement. All right.